Look off. Welcome to my video. Today what I'm going to be doing is I'm going to be reverse engineering these oil diffusion pumps. They're made by a company called VEB Hochvakuum Dresden. It's a German-based company. Let's see here. I should say it. Yeah. VEB Hochvakuum Dresden. Hergestellt in der DDR. So that means it was built in the DDR. That's the GDR, the German Democratic Republic, back whenever Germany was communist, or East Germany was. From my understanding, VEB was like a state-ran company. They did like high vacuum systems, a lot of oil diffusion pumps. What an oil diffusion pump is it is a pump specifically used for high vacuum. So uh, usually whenever you have like a vane pump or a scroll pump or a piston pump, they can only pump down to a certain level of vacuum before physics starts getting in the way, and the like the air molecules and all the little particles and whatnot in the chamber are bouncing around too much that they don't actually get pumped out. So they need something to physically capture them, and that's where oil diffusion pumps come in. It has, if you can see inside, this sort of cone assembly, and what happens is down here is a heating element. It heats up the base of the pump, and then in here in the chamber you have silicon-based oil. It's got like a low vapor point or whatever, um, and that heats up, and it kind of turns into like a steam, like a jet, vapor jet, and yeah, it expands and whatnot, and then it goes up through the baffles and then shoots out as a little jet and condenses on the wall. Here you have a sort of cooling jacket. Cold water is ran through here. Let's see here. Yeah, you have the inlet and outlet of the cooling jacket, and yeah, cold water runs through these pipes, cools the walls. So whenever you have the gas jet hitting the wall's cold, and it condenses on the wall, flows down to the bottom, and then it's like compacted or is compressed, the air molecules, and then the roughing pump, so it could be a scroll or a vane pump, connected to this output, pulls the gas molecules out of the chamber, and so you can pump down to way lower vacuums than what you could with the traditional mechanical pump. And so, yeah, these have a lot of useful applications, whether you're doing like mass spectroscopy, if you're doing scanning electron microscopes, if you're doing thin layer vapor depositions, for like semiconductor fabrication, if you're building a Farnsworth fuser or a linear particle accelerator or whatever you require high vacuum for, these are pretty good. There's other high vacuum pumps. You have ion getter pumps, which kind of like sublimate titanium and capture the all the air particles in a lattice of titanium and whatnot. Um, and then there's also turbomolecular, which those are the ones that look like a little jet engine, and they function like an axial compressor stage of a jet engine, where it just spins at high RPMs, and the molecules are basically hit down into the pump and then pumped out. The problem with turbomolecular pumps is they have a lot of moving parts, and they have to be balanced, since they're moving at such high RPMs. If they're not balanced, they're going to vibrate themselves to death. That's kind of like the advantage of oil diffusion, is they don't have basically any moving parts. So they're very robust and easy to use. However, an issue that they do have is, since they use like oil vapor or whatever, sometimes the vapor can escape and contaminate the vacuum chamber. That's why a lot of times you'll actually see these with cold heads, and it's kind of like a grating, a cooled grating, similar to this cooling jacket, over the outlet, and it allows the any escaping vapor to condense up here before actually getting into the chamber. Another thing, operation-wise, from my understanding, is uh, a lot of these oil diffusion pumps will actually have a valve up here to isolate the pump from the vacuum chamber, so you can um, release the vacuum on the vacuum chamber but maintain a vacuum on the pump. Because with oil diffusion pumps, they get up to high temperatures to heat up the oil. However, it's imperative that they operate in correct vacuum conditions, so in like rough vacuum conditions. Because if you have just a normal atmosphere, there's a ton of air in there, um, the oil will combust, and that's not really something that you want when you're uh, pulling a vacuum. And so, yeah, you got to wait for it to heat up and cool down and isolate it. So there is some pros and cons to each one of the systems. But yeah, I've got these two smaller sized pumps here, and I'm planning on selling this one actually, as well as my big one, because I don't need three pumps. And I would like to actually go smaller than this. This is already pretty small, but I'd like to go smaller. Agilent, they have the AX65 air-cooled diffusion pump, which is like the size of a soda can, which that's perfect for someone like me who's doing just small applications. So that's probably something I'll trade over to. But yeah, we're just gonna. What the plan is for today is I'm gonna go through one of these pumps, this one, and I'm just gonna go completely reverse engineer it. I've got my trusty calipers, my measurement equipment, and I got my laptop back there. Sorry, my desk is a little messy, a lot of dust. Um, but yeah, I'm gonna go through. I'm gonna reverse engineer it, digitize it basically, make a CAD model of all this. That way I have it, and then who knows, maybe in the future I can make my own designs and do who knows what with them. But it's a great learning experience. Um, and yeah, so what I'm going to do is I'm just going to kind of go through a little bit more of the functionality of this, the operation plate here, and then we're just going to begin by taking it apart and understanding kind of more about it. So starting off with the plate right here, if I can. So yeah, made in DDR. Here we have like the model number. Um, that's over Baujahr. So that's the year it was built. Here it says 1986. So this is a pretty old machine. Um, yeah, it weighs about 3.6 kilograms. Um, that's like what 1 kilo is like 2.5 pounds or something. I don't know. Um, yeah, here you have the Schutzgrad EP42. I actually, in my mechatronics book, we have that. I'm going to grab that and we're going to look at it real quick. So here in my mechatronic book, we have Schutzarten EP elektrischer Betriebsmittel. Um, so these are the different types of safety types for the system. And what we have is IP42, so that's EP42. So IP4, Drahtschutz, Schutz gegen fremde Körper. So that's like wire protection, protection against like foreign materials. And then here, that's 2 at the end. That's Schutz gegen schlagfallendes Tropfwasser, bis 15 Grad gegen der Senkrecht. So that's like whenever standing vertical at 15 degrees is safe against like dropping water. That could be like rain or like air conditioner condensation or something. Um, and yeah, so that's the safety aught, the safety type here, and then here underneath you can see this is kind of like the operational power. So you have 220 volts at 1.5 amps, 50 hertz. So in theory, the amount of power that it's going to be drawing is 0.3 kilowatts or 300 watts. So yeah, now what we're going to look at here, so this is sort of like the little junction box or whatever, and just from an outside analysis, let me kind of get zoomed out. So from an outside analysis, we have a cable feed through here, pretty large diameter, and then also another cable feed through with this metal shielding. So how we know how a oil diffusion pump operates. It heats up a heating element that's at the base and vaporizes the oil. So in theory, this is pretty straightforward. You have like a Shoko cable. That's like a 220 volt cable. It's got one. It's got one pole, a neutral, and like a ground. And it feeds through here, and then you have like a connection block, uh, like a terminal block where you plug into, and then you have a cable coming through here that's also connecting to here to this terminal block. Um, and then it goes to the coils or whatever is at the base, the heating element. So what we're going to do is we're just going to take off this plate real quick and see inside and kind of verify the theory. Alright, so I got the got it off, and yeah, here we have the little terminal. It's kind of dark in there. But yeah, you'd have a cable coming through here. You'd have a just a positive and a neutral. So L1, like a phase 1, and a neutral going here, and then here you have your ground, and the ground is connected to this kind of metal shielding, which is connected to everything else. So if you touch it, you're kind of safe in theory, because path of least resistance is going to want to go through the highly conductive metal before your slightly conductive body. So that's for a little bit for safety here. But yeah, so in theory you'd have just a power plug coming through here, 220, and just connected right here. And then yeah, we have the little aftermarket PVC feed through coming down here. What we're gonna do now is first, what I want to do is I want to take out this. Oh, excuse the desk once again, very messy. So here we have kind of the jet assembly, and we're gonna actually take this out right now and take a look at it, because this is a pretty interesting piece of technology. It's kind of one of the most important parts of this whole thing. Whenever it comes to designing of a oil diffusion pump, this is kind of like the most important geometry that you must design. So we're gonna take that out. Look at that. Okay. And then yeah, you can see inside the chamber. Yeah. So here, basically it's just like a hollow cone, kind of like something you'd see on a chocolate fountain. And if you look underneath each one of these cones, there's actually a gap there. And yeah, what happens is the oil vapor travels up through this assembly and then gets jetted out at an angle from these cones, and then it condenses on the wall with kind of momentum and downwards direction towards the output. And yeah, so how this is actually manufactured is pretty interesting, actually. You know, these vertical pieces right here is just like aluminum tubing. I'm pretty sure this is either aluminum or stainless steel. It feels very light like aluminum, so could be. There's also some cast and slightly machined parts inside of that. I'm going to actually show you that. First thing first, I'm going to take this all apart. I'm kind of one-handed right now, so I have to turn off my camera. But I'm going to take it apart, and then we're just going to kind of go through how the pieces were made and their function. Alright, so I got it kind of torn down, and we're going to start at the base and kind of work our way up through it. So here's the base piece. This actually consists of kind of multiple pieces. So first you have this cone. So the base is wider than the top, and it's kind of flared out. And so a lot of this was actually manufactured with a process called spin forming, where essentially you load up a flat piece of steel or metal in like a sort of lathe-looking thing. It's like a flat disc, and as it's spinning, you're pushing like a little tool that forms it into this kind of round, almost deep drawn sort of shape. And that's how you can get these like crazy cones and geometries, and that's how like your dog bowls and popcorn bowls and whatever are made on an industrial scale. And so yeah, that's kind of how this piece was made. And then you have these adapter pieces here. These kind of operate as like the connection points and a sort of standoff between each one of the stages. And from what it appears, this is a cast piece. There's a lot of it's kind of a rough surface, so it could be like an investment casted sand or lost wax or whatever. And then there's some evidence of slight machining work, and then of course in the middle here, that's a threaded hole. Um, and then it's got kind of a flared end to it that matches the outside diameter, and like a cutaway that matches the inside diameter, so it just pops right in. And then they drilled holes, and these are actually rivets that are holding this piece to the inside. Um, and then here you have it's kind of like a guide rod and like a mounting rod. So if you've seen standoffs in electronics, that's exactly what this is. You've got a male and a female side, and then here it's kind of milled. You have these slots milled in, so you can actually use a wrench to kind of torque it down, and it just kind of fits right here, screws into place. I'm actually gonna kind of screw it just as a little demonstration. So that screws into place right here, and now you have kind of a base to mount everything on, kind of like one of those decorative cakes. If you've seen Cake Wars, they just kind of work like that. Then we're gonna go to the second part. So this is actually, I believe, 3 parts. They're kind of stuck together because of the silicone oil. So once again, you've got like I'm not sure if this is like machined or flared or like stamped or whatever. It's kind of a more solid piece, but it acts as a standoff. It sits in these little notches right here, and yeah, so you have that, and then it goes through this spin-formed cone, and then on the other side you kind of got another standoff here, and that goes right here over. Sorry, I'm doing this with one hand. It sits right on there, and as you can see, there's a slight gap there. Now we're going to the second piece. So that goes right here. This is kind of like the piece that was stuck right here. But yeah, once again, this is like a cast piece. You can see it's kind of rough on the inside, and then there's evidence of machining on it. And yeah, goes right above here, snaps into place. Actually, really good fit. And then you have the cone, and yeah, this is just mounted in the lathe or whatever, and then spun to this form. You have like a mandrel on this side that it forms to. So you get a very consistent geometry, and you can see evidence of the spinning because there's these little kind of machine lines where the tool ran through there. It's kind of a little rough finish. But yeah, this goes up here, and it should sit right around here. And then here you've got your vertical piece, and it's kind of got this here little notch. Yeah, that basically sits there and it'll like click into place. And once again, we have kind of like the final little standoff stage, and that would sit up here. That sits up here. And yeah, keep in mind this has all got holes going through the middle. And in the final piece, this is your end cap. And yeah, first of all, they like machined a disc. They laid out a disc with kind of like this, the diameter of the screw. Sorry, it won't focus very well. Then they like chucked it into the spin formed this cone on the outside, and then threaded the screw. And the screw goes in through here, and it basically tightens up into the female side of this, essentially kind of clamping everything together, sandwiching it using this kind of one screw system here, which is actually pretty smart. And then, yeah, the jet assembly is placed in here. You can see kind of another standoff inside of there. And it screws onto there, and then at the base you'll see a ring. I'll have to measure that ring. And that's kind of where the oil from the walls, when it condenses and reaches the base, can travel back into the cone assembly, the jet assembly, and go back up. So yeah, I'm going to set this to the side, and then what I'm going to do is I'm going to further disassemble this. I'm going to take off this base plate here and kind of show you the heating element, sort of where the magic happens. So I got it inverted right now, and once again you have kind of, I reckon, from these little lines here, this is also spin formed. Makes sense if you're doing spin formed components, have multiple components spin formed to save on manufacturing costs. But yeah, you have kind of like this safety cup around the base. It's a little bit dented in, unfortunately. And then yeah, you have that feed through that goes through here. I reckon on the inside it's brazed. But you have this nut here and a little washer underneath that's kind of holding it flat onto here. So what I'm going to do is I'm going to take off this nut, pull this off, and then we're going to see on the inside. I've already taken it apart a bit on the inside. So some stuff is already taken off. I have a picture of it all like assembled. So I'll show that, and then yeah, you'll see the inside, and we'll go through that a little bit more. All right, so here's the inside. As you can see, you've got this little feed-through bolt thing here. Yeah, so these are wires that come from like little junction box, terminal box thing. They're shielded. They've got little ends on them, little ferrules or whatever. And then here you've got the ceramic kind of terminal block. So it's ceramic because ceramic's an insulator. You don't want it to short through here. And yeah, that basically connects these two leads to these two leads. And these two leads actually go into here to these little heating element plates. Now, there's an insulator. There is it's a thermal insulator between the heating plates and kind of this mounting plate here, and it looks an awfully lot like asbestos. So that's got me a little bit worried. So I'm going to be cautious, but yeah, I'm going to take this apart further, and I'm going to show you a little bit more. And yeah, let's get into it. All right, so I've got it taken off here. I don't want to take this apart too much because of the whole asbestos thing. But yeah, you've got the mounting plate above, kind of acts like a giant washer, and it's also where you mount this terminal block. And then underneath it is where you have your like asbestos thermal insulation. And you have like another mounting block, and then you have these two kind of flat plates. It's like almost a phenolic metallic resin type deal. There's looks like a little cherry rivet right there holding the two plates together, and I assume this is a heating element. I'm gonna have to conduct some more research on exactly what kind this is, because I've only seen like the nichrome wire heating elements. So I'm gonna have to see kind of, maybe this is like an older technology that I'm not familiar with. But yeah, I'm gonna go through this piece later. I'm gonna model up like the little plates and everything for my 3D model. But yeah, just taking off this piece now. I'm gonna set it over in a safe place on my messy desk. And now we're coming back here to take a look at this. So here, yeah, you have this feed-through bolt, and this bolt is the same bolt that we saw actually on the inside of the chamber where the jet assembly actually screws onto. So from just looking at this, and I've measured this earlier, the construction of this is basically you have, I believe it's like maybe like a copper coated stainless steel. I'm not quite sure of the metal's composition. It'd be very nice if I had like a XRF spectrometer. But essentially how it goes is you've got this metal tube here running from the flange to about this little welded point. Just like I believe it's got a welded seam on the inside. Yeah, there, if you can kind of see it. Sorry, my lighting is horrible. Or, let's see, it's in there somewhere. Yeah, there's just this long seam running axial down the tube that's welded. Forms a tube. And then on the bottom of the tube, here, you can see it's welded. you have an end cap, and now I'm pretty sure this end cap has sort of the same lip situation as a lot of the other pieces, where it's kind of got a little step where the inside part of the step is like you have the matching inside diameter of the pipe, and then the outside step is matching outside diameter of the pipe, so it just kind of snaps into place, and then you can weld around it and you have more surface area. Um, and then in this end cap, you have a hole drilled through there. Now, it could be, I'm not sure if it's threaded or not, but it's definitely brazed. You can also see kind of the heat discoloration there. And yeah, you can see down here is the other side. It's kind of like a similar standoff bolt where you got one side that's male, one side that's female. But yeah, that's kind of like the main part of it. Now, you have this lip, once again, most likely spin formed. And this is just welded on the outside diameter here. You've just got kind of some rough welds there. They don't have to be vacuum tight, so it's not too important. But this is where this kind of safety cup on the outside attaches to, pushes up against there and kind of creates a sealed housing. So that's all fine and dandy. Then more kind of cosmetically, you've got this bracket here, this bent metal bracket, and it's also just kind of roughly welded or brazed into place. And then you've got two bolt holes for this plate here that mounts on, and then the junction box mounts to this plate, which feeds through here. Then here you have these kind of nuts here, right here, and what I'm pretty sure, because looking inside, there's nothing that passes through, and you know, you've got the cooling jacket right here. It's not connected to here, so I'm pretty sure this is just like a mounting point, or actually what this could be is a point where you mount your thermocouple to. That could very well be it. You mount a thermocouple here, and then you can monitor the temperature of the pumps for operation, so you're not introducing the atmosphere whenever it's too hot or whatever. So you have that. And then, yeah, that's just kind of brazed on here. Or actually, you know what? It could be brazed. I'm not really seeing too much evidence of that. It could be a light braze, actually, because yeah, there's really not a lot there. I don't think it's cast into this, because once again, I said this is like kind of like folded and then welded on the inside, so it wouldn't really make sense to have that casted or anything. But then, yeah, you have the threaded nuts with a hole going through one side. Then you have like a copper tube brazed into there, and then it's brazed on this side, which seals it all up. And then it's wrapped around the whole thing. Then same thing on this side. And then they add some braze on here to connect it. And then you have kind of like this aluminized, metallized coating on the outside. And then, yeah, going to here, you have a flange. I'm actually going to do some research and get into what type of flange that is. I'm pretty sure it's an ISO 63 flange, just judging by the geometry and how it's like clamped and everything. And then, so that's like kind of the main assembly body here. And then now we're going to go off this like feed off the spigot thing here. Sorry, my vocabulary with these pumps is pretty limited. This appears to be like it looks kind of like a rough cast surface, but it could also just be like a bent pipe, bent piece of tubing. Yeah, it's like welded here, pretty thick welds, and then here you have this kind of it's like a KF flange welded to the end of it. I'm gonna have to measure the diameter and then determine exactly which KF flange this is. But yeah, that's just kind of where the roughing pump connects to. And yeah, so that's basically like a quick run through. Oh, I can't set it down on that side because it doesn't have a base. So that's a kind of a quick run through of it. What I'm gonna go through next is I'm gonna fire up my computer, and I'm just gonna go through piece by piece and model it up, and I will, like with each piece, I'll kind of show you the finished version, and then if I'm doing like measurements or whatever, like I'm gonna use my calipers and measure the outside and inside diameter of this pipe and this end cap and this piece right here. I'm gonna use my ruler to measure the depth of it and then the total length, and then I can subtract the total length or the depth from the total length and find out the end cap thickness here. I'm just gonna go through, reverse engineer everything and just kind of go through the process of it. But yeah, let's kind of get into it. Okay, so I measured the outside diameter of this end piece and the outside diameter of this little pass-through hole, and I put it into my CAD software here. It's just free CAD. And then what I'm going to do is I'm going to make this however thick this piece is, and then I'm going to do a little cutoff function here, and then we're just going to move on. Alright, so the base plate's done. Now we're going to move on to that little ring inside of there. Alright, the standoff ring that you can kind of see in there, that has been modeled. Now we're going to move on, probably this main body section here. Alright, so right now I'm just modeling the main body, main tube. I've got like the feed through hole, the roughing pump and everything. What I've decided on doing is anything that's kind of welded on, so this thermocoupled piece right here, or the vacuum or the cooling jacket inlet and all that stuff, anything that's welded on flanges, that's going to be modeled separately. That so later, should I decide to machine this, I can have the bare model for each of the pieces, and then I can assemble it later. But yeah, so here I just got the tube basically done. Next part after the tube, it will probably either be this piece right here or one of the flanges. But yeah, so right there I just have a datum plane, and then that's how I did that feed through hole at the base. Okay, so this ring right here, that kind of holds this protection cup on the back. Got that modeled in, and yeah. So next will probably be the spigot here, or maybe this cup. Gosh dang. Yeah, maybe this cup. And yeah. Alright, we got the little spigot piece modeled up. Next will probably be the flanges. Alright, so the flange has been modeled up. Then we're going to the little KF65 flange down here. Alright, so this little KF25 flange has been modeled. Base cup is finished. Now we're going to move on to the next piece. Alright, so now I've got the cooling jacket tubing modeled. Next will probably be these fittings. Okay, you got these little fittings all catted up. I didn't do the threads, those can just be put in later, so it's not too important. But yeah, just the general geometry I have it modeled. Alright, so I've got this guide rod that's kind of in the back of the chamber right there. Got that all modeled up. Protrudes out the end here. That's to hold on the safety cover for the heating element, and it also acts as kind of like a guide for the jet assembly. Okay, so I've modeled the jet assembly here. It is a very difficult part to model. Whole bunch of sweep functions because it's spin formed. I believe it's aluminum or steel. But yeah, pretty complex. We got that done, and now we're going to move on to the heating element. Alright, so here we got the heating element. It's actually, sorry, this is pretty heavy. It's actually a mica heater. So it's these two flat plates here. Look sort of like a phenolic resin covered with a metallic coating. It's a mica heater. It's an older style heating element, super flat. Okay, so we got this all catted up here as well. You can see the different plates and the pass-throughs and everything. And yeah, that's pretty much the pump complete. If you're interested in the CAD model, it'll be linked below the video. Also, if you're interested in buying one of these pumps, I'm gonna have the link to eBay They're gonna be around $100 plus shipping, which is a pretty fantastic deal for an oil diffusion pump. So, yeah, if you're interested in buying one, take a look at the link. If you want the 3D model, that'll be made free. And thank you for watching.